Hi, everyone. Thank you for coming back on day 3 of Swee Hong's talk on combinatorics atlas. And today he's going to talk about some applications on Stanley's poset inequality. All right.
Thank you very much for the introduction, Anna, and also thank you everybody for coming, and also thank you for people who are watching the recording. So today we are going to continue on the application of combinatorial atlas, and we will focus on the application to Stanley's poset inequality today. So by a poset, I mean a partially ordered set. This is a set where the ground set we will write it as X, and it will have a partial order on the elements. So, for example, this picture here is a poset of 4 elements, A, B, C, D, and these arrows is define a partial order. For example, an arrow from A to B means that A is less than B, A is less than C, B is less than D, and C is less than D. And by the way, there's actually one other arrow that I don't draw, which actually is implied by transitivity, that A is less than B. Because A is less than B, B is less than D, by transitivity, A is less than B. But we don't draw it because it's redundant. Okay, this is called the Hasse diagram of the poset. And we will also use N here. This will denote the size of the poset. Okay. And the object of the poset that you want to study today is what we call the linear extension. This is simply the completion of the partial order. For example, for this poset, there are 2 possible ways to complete it into a total order. Either A less than B less than C less than D, or A less than C less than B less than D. And log concavity appears very naturally in the poset in the following way. First is that throughout all these talks, Z will always be fixed. It will be always a fixed element. Let Nk, this is a number of linear extension with Z being the k smallest element. And it was shown first by Stanley in 1981 that this sequence N1, N2 up to Nn is a log concave sequence. And this inequality is proved in a very elegant manner. It's basically a one-page proof. It was what Stanley did is that he interpreted all of this number as the mixed volume of something that's called the order polytopes. And then they plug this into the Alexandrov-Fairchild inequality, and magically this theorem just follows, that this log concavity just follows. Okay, in fact, let me just say for today, you see here that I put the word simple case. This is because Stanley actually proved Stanley's inequality in a greater generality. And today we will only discuss the simple case, but on the day 4, Igor will discuss the full generality. So let me just make this as what you call the preview for what happened in day 4. And here's an example of an application into algebraic combinatorics. So consider the Wick-Buchard order on the permutation group. This says that pi is less than sigma if the inversion set of the pi is contained in the inversion set of sigma. Okay, so the standard one. And for any fixed permutation sigma, nk sigma is a number of permutation that is less than sigma and such that pi1 is equal to k. So the first element is mapped to k. In general, you can take 1 to be any I, this result will still work. And it follows directly from Stanley poset inequality, because this actually defines a certain poset, that this sequence n1 sigma up to nn sigma is a log concave sequence. And to the best of my knowledge, there exists no direct proof of this result yet. That in fact, the only way we can prove this log concavity is to actually interpret it as Stanley poset inequality and then get this result. There is no other proof. And there's no direct proof. And if anybody ever find a direct proof of this, please let me know. I'll be very interested to learn. Okay, and the goal for today is that we are going to prove this Stanley poset inequality not by using Alexandrov-Funchal inequality, but by using combinatorial atlas. And after that, we'll also try to prove something more. But before we proceed further, are there any questions about the setting, about the number? Yes, I saw.
I read your introduction to combinatorial atlas, and you gave a proof of Alexandrov-Funchal inequality using combinatorial atlas. Is that somehow related in your disproof of Stanley's inequalities?
That's a very good question. Yes, that's actually what is going on. First, actually, we find the proof by Alexandrov-Funchal inequality first, and then we realize that you can do the same thing for atlas. For poset, but for the poset case, you can actually do even more. First is I will explain what is the more thing in the end of this talk. But thanks for the question. Any other question? Okay, if there are no questions, then let me continue the proof. And as usual, the proof will involve building an atlas and then say that this atlas satisfies the hyperbolic property. Okay, but before that, I want to have a slightly change of way to view linear extension. I want to claim that, in fact, I want every linear extension, you can view it as a word. That means as a string of letters, where the ith word, the ith letter, will correspond to the ith smallest element in the linear extension. So for example, for this poset, we know that from the previous example, there are two linear extensions, and the two words corresponding to these two linear extensions will be ABCD and ACBD. This is just just another way to present linear extensions. And by using this this nomenclature, we will now define the extension matrix. Okay. First thing is that I will say we need to fix the k, the value of k, to always between 2 up to n minus 1. The reason is because if we go back to Stanley inequality, the log concavity is only non-trivial when k is of these values, because otherwise either nk plus 1 or nk minus 1 is always 0, and the log concavity is always true. Okay. So that's why we will just assume just for without loss of generality, that k is inside this range. Another thing we want to make assumption is that we'll assume that x1 up to xl, so there are the minimal elements of the poset. So this means that there are L many of them. And we'll assume that xl plus 1 up to xn, this will be the maximal element. So this means that there are m minus L maximal elements, there are L minimal elements. It's a sum notation because otherwise then things get really messy really soon. Extension matrix, I define this to be EPK. This is the matrix. There are 3 different cases. We will first look at the cases when I is contained in L, so it corresponds to the minimal element, and J corresponds to the maximal element. This will be the number of linear extension such that the smallest element will be omega 1, and the largest element will be omega n. This is why we need 1 to be minimal, we need J to be maximal. And we also want the Z to be the k smallest element. Okay? This is how we take Z into the input. Just up to this part, any questions so far? Before we go for the definition, will involve 3 parts, unfortunately. Okay. Next thing. So now let I and J, they both correspond to the minimal elements. EPKIJ, when I and J are different, this is number of extension. The first smallest element is the omega 1. The second smallest element will be xi. Xi corresponds to the smallest element. Xj corresponds to the second smallest. And now you see that the value for Z increases by 1. It becomes k plus 1. This is because so that in the end we can get log concavity. So that we can get something that corresponds to k plus 1, k, and k minus 1. Okay. And what is important here is that you see that the diagonal elements, the II, this is number of link extension such that xi is equal to omega 1, and omega 1 is strictly less than omega 2 in P. remember that for the case of matroid, the diagonal is always 0. Diagonal is always 0. This is because in a way the matroid is a commutative object, that there is no order involved. But when you go to poset, you see that the order actually does matter, right? That's why it has a total order. That's why this definition is included. That's why this number is non-zero. And this is the only way to make the proof work. If we skip this way, if we let diagonal to be 0, then the proof will fail. And in fact, there's the fact that this diagonal is non-zero. Maybe let me just give a spoiler. At the end of today's talk, we will see how this impacts some of the results, that it actually makes some differences. Okay. And finally, the definition part 3, this is when both I and j, they correspond to maximum elements. This is as a dual to the previous part. That rather than xi is now equal to omega n, xj equal to omega n minus 1, the number j decreases from k to k minus 1. Okay. So this completes the definition for extension matrix. And here, let me just make a maybe small remark, which is that in a way, it's a bit ironic that you see that for matroid was proved, what do you call that, the Mason's inequality and the Sota conjecture, it was proved in 2020. And while this Stanley's inequality was proved in 1981. But once you make it into atlas, somehow the matroid one is actually the simpler one. The one for this poset inequality, the matrix actually needs to be more complicated. Okay. But other than that, are there any questions for the definition of extension matrix? Okay, good. Okay, and let me just give an example. So here is a poset of 5 elements. Z is this element in the beginning. The extension matrix will be this 4 times 4 matrix, where the element that corresponds to to 1 and 4. So this is this element 2. This corresponds to the linear extension, where x1 is in the beginning. This is for 1. x4 is in the end. This is for 4. And z is in the position number 3, because k is equal to 3. The same logic apply to all of this, except that you see that when 1 and 2, they are both minimum elements. That means that the fixed element will be x1, x2 at the beginning. And when they're 3 and 4, when they are both maximum elements, the element that got fixed is at the end. Okay? And as you can see in this matrix, the only, so this is a coincidence that this one becomes 0, but otherwise the non-diagonal entries are never 0. Up till here, are there any questions about the definition?
I forgot the definition for the position of the z. So is it like if you have x1, x2 in front, then I treat it as like one object, and then so the z is on the 3rd position in the 2nd line, because like if I count, it's the 4th, right?
Exactly, yes. Actually, maybe one way is that you just think of the 3 minus 2. You just remove this element, remove all of this blue color thing, and the position of z will always be position number 2.
I see.
Because of k minus 1.
I see, but it is not the same when it is like II, right? Because like the 3rd row.
Yes, for II, we actually need to take x3 as fixed because x1 is less than x3.
Okay.
Yeah, it's a bit, unfortunately, the base is a bit complicated, but this is the one that works. Okay. In fact, maybe let me just add one more word, is that there's actually a complexity theory reason why this matrix will be this complicated, and that will be proved in day 4. Okay, and as usual, our goal is to try to prove the hyperbolic property, which says that given any matrix, given any vector x and y, the inner product of x times my square is greater than x times mx times y times my. And this is the same as we have known, as is discussed in the previous 2 lectures. This is the same as saying that m has at most 1 positive eigenvalue. And this is the property that we want to prove for today. And the claim for the extension matrix theorem is that this matrix EPK that we defined from the previous slide, this matrix always satisfies the hyperbolic property. when k is between 2 up to n minus 1. Is not inside this range, then the matrix is not well defined. So we just say nothing. But in that case, the log concave inequality is also trivial. Okay. And if no question, I will show how this theorem implies Stanley inequality. The idea is that you take x and y to be this vector where the first L entries, so this is the first L entries. The first L entries is equal to 1. The last n minus 6 and n minus L entries is equal to 0. While y is the opposite, which is the first L entry is equal to 0, the last n minus L entries is equal to 1. And that it follows from definition. That's why we define the matrix M in a very specific way. X and y will be equal to nk, xm x nk plus 1, my is nk minus 1. Then the Stanley inequality, at least a simple form, thus follows immediately from the hyperbolic inequality. This is the reason why we want to prove extension matrix theorem. Before we continue, are there any questions? Everybody happy? Okay, everybody's happy. I'm happy. Let us continue. And to prove this extension matrix theorem, we will use the extension F plus, as usual. And as a recap, an F plus, this is a collection of D plus 1 matrix, M0, M1 up to MD, at a fixed vector H. Okay. And M0, we will call it as the parent of the atlas. And M1 up to MD, this will be the children of the atlas. And we want to show that all of these matrices satisfy the hyperbolic property. And in particular, it implies that our extension matrix satisfies the hyperbolic property. That is what we want to do today. Okay. And the way we do it is as follows. First is that we will need to define what is the atlas, at least for the poset case. So first, you fix T to be equal, to be strictly between 0 and 1. This is so that the vector H will be a strictly positive vector. You fix K, you see here I put K to be equal at least 3 rather than 2. This is for a reason that I will explain soon. But now you first define M0 to be the interpolation between EPK and EPK minus 1. And MI, the children, this will correspond to the poset where you reduce one of the elements. So you delete one element and reduce the value of k to k minus 1. Okay. So this is similar to the atlas that we construct in the day 1 and day 2. Just that we change the definition from the matroid to poset. The one difference here is that you see that here I assume k is at least 3. This is because if I put 2 here, then k minus 1 will be 1, and then this matrix will be it's not well defined. That's why this k needs to be 3. Okay? For a technical reason, and you see the technical reason very, very soon. Okay. Now, wait, sorry, maybe I go, any questions so far for the definition of extension atlas? Everything good? Okay. And now the usual way we prove this thing is that, again, we want to use the children to parent principle. The idea is that if your atlas satisfies certain properties, all of these properties are very easy to verify. We verify them in day 1. That if this atlas, if the children satisfy the hyperbolic property, then the parents will also satisfy the hyperbolic property. Right? And then we use that to use induction to then prove that everything in the atlas, the extension matrix theorem, is true. Okay. And here let me just make one remark, which is that here you see that there's this property that's called decreasing property. I put a cross here. The reason is that because unfortunately, because our poset case is more complicated, this decreasing property is too restrictive. That is not true anymore for the extension atlas. That's why we substitute it with 2 properties, the projection and k non-negativity. I will not explain them today, but let me just promise you that these 2 properties are also not hard to verify. Okay. Okay. Now let me prove the extension matrix theorem. And we will use induction on n, on the size of the poset. The base case is actually equal to n equal to 3. So this is the poset of 3 elements. And I checked that there are actually 15 many poset up to isomorphism. 15 many poset of 3 elements. And what we do is that for those 15 poset, we just check all of the metrics. And it turns out that up to isomorphism, and then you also throw out the 0 rows and columns, you see that there are exactly 6 of them here. Then after that, what I do is that I run Sage, I plug in every single one of these metrics, check their eigenvalues. Oh, what a coincidence. All of them satisfy hyperbolic property. And actually, also let me just add that there's actually a combinatorial way to show all of this, rather than just a brute force, but brute force is also possible if it's 6. Okay. So this proves the base case. Okay. Now let m to be greater than 4. And now assume that k is between 3 up to n minus 1. Otherwise, then the application F plus is not well defined. Then, by induction, all of the children of the atlas satisfy hyperbolic property. So by the children-parent principle, the parent M0 also satisfies the hyperbolic property. Okay. And this is by definition equal to this big matrix, right? And just like in the case for the matroid, you take t goes to 1, then you will get that EPK satisfies the hyperbolic property. And in the matroid case, that is where we stop. Then we are all done. But here in poset case, there's actually one small technicality that we need to be careful. This is because in the matroid case, your k can be any value. That's why we don't need to do anything anymore. But for poset, you see that k is at least 3, right? So if I plug in k equal to 3, you will get hyperbolic property for EP3, EP4 up to EPn minus 1. But remember, if we go back to the statement for our extension matrix theorem, this is this one. The value start from 2, but they start from 3. So there's one case that we still need to check. And the way to fix that is that this is let me go. Oh, sorry, this one. The way to fix that is that you take t goes to 0. Then you will also get that APK minus 1 satisfy hyperbolic property. Take k equal to 3, then you get EP2. That is how you cover all values. This is a very subtle detail that in the big picture, it probably, in the philosophical level, it probably does not matter. But when you prove this thing, this is one of those small things that will trick you. That's why I spend some time to explain it here. Okay. And let me also just add one thing that actually, even here, I already cheated a little bit. This is because if you go to the proof in the paper, you will notice that the children-parent principle, it actually fails in some edge cases. That there are some cases where one of the 6 properties that we need to check, some of them fails to hold. But for those edge cases, there are some tricks like taking dual poset and taking some poset, like just removing some extra minimal elements that will actually give us back into this case. So that's just, so let me just make a reminder that maybe just make what they call that disclaimer that things is a bit more complicated, but the big picture works like this. Okay. Any questions so far? I think that is the proof for this theorem. Any questions so far for this theorem? Everybody happy? Okay, so everybody's happy. Let me continue. And so in the end, after we gather everything and write them down carefully, what we have shown is that this Stanley's inequality that was proved in 1981. Now we show it a new proof that shows that this sequence is not concave. Okay, and it is true that let me just say that one thing that Stanley proof is actually, in a way, is better than our proof because it's much shorter. It's 1 page. Our proof is like 6 pages with some complicated definition. So if that is the, so how to say that, right? There must be a reason why you want to introduce a complicated thing over something more simple, right? And the reason why is that this new technique is now possible to solve the Stanley's equality problem. And this is what we are going to discuss next. Okay. So this problem was actually started by Stanley in the original paper, where he asked that, can you find equality condition for the Stanley's inequality? And by the way, let me make a very important remark here. You see that I put Stanley's inequality in a box. The reason is because Stanley does not call this inequality Stanley's inequality. In fact, even to this day, in some private conversation with Stanley, he always refers to this Stanley's inequality as a Chern-Fishburne-Graham conjecture. Okay? I think it's because he's a very humble person. And the reason why he called it Chern-Fishburne-Graham conjecture is that this inequality was first conjectured by Chern-Fishburne-Graham. Okay? So that is how Stanley attributed to them. And there is an important reason why Stanley asked this question. This is because whenever you have an inequality, those inequalities that you have equality conditions, they usually show that you have achieved a next level of understanding. It shows that you really understand the inequality, and not just because you get this inequality for some using some tricks. That's why Stanley asked this question. Okay? That is why people try to prove equality conditions. And so this question, Stanley's equality problem, turns out to be a very difficult question. In fact, it took like 50 years before it was finally solved by Sandler and Van Handel in 2023, where they show that equality can occur if and only if these two conditions happens. The first condition is that you look at all elements x that is greater than z, and then you check that the number of elements less than x, which is the size of the order ideal, is greater than k, and you do the same for the element when x is less than z. So it is a dual condition. Okay. And the condition itself is a bit complicated, and the detail is of course important. But what is more important is that this condition is a combinatorial condition. What it means that this condition really describes those posets for which the equality holds. It gives you a description of the combinatorial structure, not the geometric structure, right? Because this will also be important in the next talk in day 4, is that this thing is actually very efficient to check. That not only that it's combinatorial, it's also very efficient. It can be checked in n square steps. Because you see that these steps involves checking at most n many elements. This number can be computed in n times. So in total is n squared. Okay. And one more thing I will add is that, actually maybe I already say that this equality condition, it actually has a very important complexity theory implication. Maybe a bit of spoiler, it will actually show that Stanley's inequality cannot be proved in any nice combinatorial manner. That more or less the Atlas proof and the mixed volume proof is the best you can get. Okay, that will be discussed in day 4. And the key to do that is understanding the equality conditions. But in any case, for today, we will not focus on the complexity part. We will only focus on giving a new proof of this result. Okay. Or maybe I think I forgot to say this, but let me go back. By the way, how Stanton and Van Handel did this is also very nice. What they did is that they first established the equality condition for the general Alexander-Fenchak inequality for convex polytops. And then after they did that, after they spent a very long, like a 60 pages paper to prove this thing, and then at the end, they apply their theory to get the equality condition for the Stanley's inequality. And our goal today is to give a new proof that is a bit simpler, a bit more combinatorial. That maybe does not require 50 pages, but maybe like 5 pages. or maybe 5 slides. Okay, that is what we are going to do next. Before I continue, are there any questions? No? Okay, then let me continue. So we will prove the equality condition. And to do that, I will need to introduce a new property that's called the hyperbolic equality. This condition is saying that given a matrix M and vector x and y, we say that this triplet satisfies the hyperbolic equality if x and y square is equal to x and x times y and y. So this means that you have equality in your hyperbolic inequality. Okay. And notice that this is actually just a special case for Stanley's equality. Because remember, by using these choices of m, x, and y, these three values can be written as nk plus 1, and nk minus 1 in Stanley's inequality. So then, having equality in Stanley is the same as having a hyperbolic equality for this specific choice of m, x, and y. And in particular, if you want to prove Stanley's equality theorem, it will then reduce us to understanding the hyperbolic equality for at least many of the applets. That is the idea. Okay. And the way to do this is is the opposite of how we prove hyperbolic inequality. Remember that for hyperbolic inequality, we prove it like this, right? Every children got COVID. Every children got hyperbolic inequality, the parent got it. But here, for equality condition, it works the different way. It works in a different direction, in the opposite direction, which is that when the parent satisfies hyperbolic equality, then all of the children, no, not all, sorry. Most of the children will also satisfy the hyperbolic equality. The idea is that maybe just if you are just given one equality, right? One equality for one inequality. That might be complicated. But by using this, you can inherit this to all of the children. So now not only that you have one equality condition, you have many equality conditions. And the more you have, the easier it is to recover the whole picture. The easier it is to recover the combinatorial structure behind the equality. That is the philosophy for this parent to children principle. In a way, it's a bit like what my grandmother, a conversation with my grandmother. So my grandmother has 8 children, and back then as a kid, I asked him like, grandmother, isn't it very hard to have these many children? And then my grandmother said that, Swee Hong, you don't understand. You know, we already have 8 children. You just ask all of these children to actually go to the first children will take care of the second children take care of the third children, and so on. That is the same idea here, that you use this when you have hyperbolic equality, you transfer it to the children and use these children to solve the whole problem. Okay. Okay. So now let us see how it got used in mathematics. Okay. So again, recall that what we want to do is this, right? We want to prove the Stanley's equality theorem that equality occurs in the inequality and only if this combinatorial condition holds. And for today, we will only prove the right direction, that A implies B. This is because the second direction is straightforward, that if you're given this, you can check just by definition, just by calculation, that these numbers must be equal. So it's only the left to right direction that is non-trivial. Okay. And to prove this, we'll use induction on n. Again, the base case is n equal to 3. In this case, there are actually, I checked, there are 11 possibilities for this theorem, that PKZ. And 11 cases is not 200. It can be checked by hand. You can check that it's confirmed for all of them. And now, for the case n greater than equal to 4, we'll use Atlas method to prove this. And here, what I want to, first thing is that for the Atlas, we will take the Atlas when P is equal to 1. This is so that the parent is the matrix EPK rather than a matrix like EPK plus 1 minus T of EPK minus 1, right? This is the one from before. But we only want to do this when T is equal to 1. This is because the hyperbolic equality will only hold from for this matrix EPK, but not necessarily hold for EPK minus 1. That's why we need to take the case T equal to 1 here. Okay. And now let X and Y is the same vector as before. Then Stanley equality implies hyperbolic equality for the matrix M0. And then by the parent-to-children principle, my grandmother then the parents create all of the children. All of these children also satisfy the hyperbolic equality. But see that this is now for Mi rather than M0. Okay. Now recall that X1 up to XL, this is just the minimal elements of poset. I will write Pi to be equal to the poset P, remove the minimal elements. Then this previous slide, this inequality, hyperbolic equality, by the definition of the matrix Mi, this is equal to say that nk minus 1 square for the Pi is equal to nk times nk minus 2. Notice that this is for the smaller matrix Pi, not for the matrix P anymore. And also notice that k becomes k minus 1. This is because if we go back to the definition of the the number here is k minus 1, not k. That is a detail that is important for the induction. Now, notice that this matrix Pi is a smaller matrix, right? So the number becomes n minus 1. So now we can use induction. In particular, implies that this condition is true by induction on the smaller poset Pi. Now notice P greater than X and Pi greater than X. These two posets only count elements that is greater than X. Because Xi is minimal, this means that it will never counted in any of these two posets. And therefore the number must be equal, whether or not you remove the minimal element. Right? Because minimal element cannot be greater than X, strictly greater than X. By the previous slide, this is greater than this number, Pi minus k minus 1 plus 1. But Pi is equal to P minus 1. So this is equal to P minus k plus 1. And then for this argument, you do it for all X. That gives you the first combinatorial condition in the Stanley's equality theorem. And then you just do the same thing, but for the opposite, you do the when you just change all the signs of greater than equal to less than equal, you will get the second condition. That is our simplified proof. That's our new a different proof of the Stanley's equality theorem. Okay, that is how this is this theorem. Up till here, are there any questions? Everybody happy? Okay, if everybody is happy, then maybe let me continue. And today, I understand that for the last 3 days, we have been keep talking about log concavity, log concavity, log concavity. So today let me change our the flavor a little bit to a new topic, which we call the approximate independence. This concept was first introduced by Jeff Kahn, who is my colleague here in Rutgers, and he first defined this for the matching. So given a graph G, let Mg be the number of matchings of a graph. But Kahn proof for the number of matching is that this inequality, that this ratio is between 1/2 and 2. And the reason why we call this approximate independence is the following. These numbers, let me do it this way. Mg minus X, this number is equal to 1 over the probability that X is contained in M, where here M is the random matching of G. random matching of G. So this ratio is the same as the probability that X and Y, both X and Y appear in M, or sorry, let me write like this. Probability that X appear, oops, sorry. Let me go back to the slide. So this ratio is equal to the probability that X in M and Y in M divided by the probability that X in M times probability that Y in M. In particular, if this number is equal to 1, then this is exactly the definition that these two events are independent. But as Kant observed, this number is not always equal to 1. But then we can actually aim for something that is a bit less than independence, which is that this number is between 1/2 and 2. And then after that, Jeff can show that even without independence, even with just approximate independence, sometimes you can still use it to prove many of the equivalent results. And he used this to prove several results in the hardcore, what do you call that? Hardcore model. So in this population model. And here's a quote by Jeff Kahn, which says that, no, sometimes we cannot achieve exact independence, but we do still have considerable approximate independence. And that is usually, that is sometimes enough to prove many interesting results. Okay. And let me just make a disclaimer here that this statement is completely a mathematical statement that we do not endorse, and this is not supposed to be taken as a political statement, and we do not endorse any political view, any political leaning one way or another. Okay, completely a mathematical statement. Okay, and this approximate independence is in 2022, it was extended, or maybe it was proved for matroid by Junhe, Schroeder, and Wang. What they did is that let Bm be the number of bases of matroid, and they saw that the same ratio is also less than 2 times 1 minus 1 over D. I forgot to say that here D is the rank of the matroid, the rank of M. And as far as we know, we do not have any example for which this is equality. And the largest ratio that we can get for this so far is 8/7. And it was conjecture that, okay, it was not conjecture, but I think some people believe that this inequality can be improved up to 8/7. But unfortunately, nobody has been able to do that yet. Okay. This is matroid. And the one that we are interested for, the one that we will prove for today is the one for the linear extension. So let EP be a number of linear extension. Let's look at this ratio where X, Y are the minimum elements. We claim that this number here is between 2 and n over n minus 1. And unlike the other two examples that we saw for the matching and for the matroid, we do know that this inequality is tight in both directions. The lower bound, it was first proved by Spitzberg in 1984. We proved it by using FKG inequality, and this is tight for anti-chains. While the upper bound was proved by me and Igor in 2 years ago, 2022. And as far as I know, this is the only way to prove this by Upler's method. There is no other way. And we also show that this is tight for anti-chains of 2 elements. And so this is, in a way, it's very rare that unlike the other 2 cases, or unlike for the matroid, these two, some people believe they can be improved to 8/7, but for the poset, this cannot be improved. And one of the technical reason why that is the case is because of the definition for the extension matrix. If we go back to the extension matrix, let me just go back there. You see that the diagonal entries is rarely zeros. While for the matroid case, if you remember from the previous classes, the diagonal entries is often to be 0. This difference actually reflects in the proof, and that is the reason why we can achieve we can achieve the strictness for the poset. But you can achieve tightness for poset, but not for matroid. That is the technical reason. The philosophical reason is slightly unclear. I mean, yeah. But I hope, but before we prove this theorem, are there any questions so far about the independence? Yes, questions.
Is the equality case for this inequality, is it if and only if or
That's another good question. We don't know if it's if and only if.
okay.
That is still open.
Thank you.
Unfortunately, yeah. Okay, they have no question. Then let me show the proof, at least for the upper bound. The lower bound is by FKG, so that is beyond the syllabus of the lecture. So, but it's also that so that let me not cover that and only cover the proof of the upper bound. And the proof goes like this. So one of the consequences of the hyperbolic property is this property that we call the true independence, which says that if the matrix M satisfies hyperbolic property, then for all non-negative vector Vxy, we have that Vmv times xmy will be less than 2 times Vmx times Vmy. Okay. And this inequality actually, we proved this inequality for the R+ case in our paper. But in fact, you can say that this inequality is already like implicitly known, like maybe even from 1920s. In the case of the mixed volume, this is actually a consequence of the what we call the Steffer inequality, or sometimes also the Farber inequality. And I might have spelled this name correctly. So, and the same principle also applies to this to the situation where Junhe and his co-authors proved the proximate independence for matroid. The details are different, but all their philosophies are the same. Okay. And the proof goes like this. Let P prime, this is the poset. You take P and you add an extra element Z that's incomparable to all other elements in the poset. Okay, and as you set your M to be the extension matrix for P prime, V is the matrix where the first L entries is 0, last M minus L entries is 1. X, this corresponds to the first minimum element, Y corresponds to the second minimum element. Under the assumption that the element X in the theorem is X1, the second element is Y. Okay. Now you plug this into this definition into Vmv, Vmx, and Vmy. You will see that this number O is that, oh, what a coincidence. Just by definition, this will be equal to EP, EP minus X, and EP minus Y. And the last one, EP minus X minus Y. Then you just plug this into two independence, then the approximate independence follows immediately. Okay, so this is just an easy consequence of this property that we call the two independence property. Up till here, are there any questions? No question, then let me continue. So in the end, what we have done is that we prove the approximate independence for the poset, and unlike for the matroid, and also unlike for the matching, the lower and upper bound is actually strict. It's actually tight. That this cannot be improved anymore, fortunately or unfortunately. Okay. Anyway, I think this actually concludes the lecture for today. In fact, also conclude the lecture on my end. So for the next episode, for the next day, it will be done by Igor Park, my co-author. And the preview is that in today, what we have done is that we proved Stanley's inequality for the simple case, and we also proved the equality condition. And in the for day 4, one of the things that Igor will discuss is that he will discuss not the simple form but the generalized form. So the full version of Stanley's inequality, and he will discuss how you can use the equality condition and complexity theory to show that in a way there is no easier that there is no combinatorial proof. There is no easy combinatorial proof for Stanley's inequality. That is what one of the things that eager will do on day 4. Okay. And I think that's all I want to say for today. Thank you very much for listening.
Thank you so much. Any questions? I have one. So like, I think it's quite earlier in the slides that you have a condition that you cross out and then you said you replace by 2 other conditions. And so, does the one that you cross out implies that you satisfy the 2 conditions?
That's a good question. Yes, let me go here. This is the children's parent principle.
Right.
Yes, the atlas for the poset does satisfy these 2 new conditions. Yeah, the
I
cross
see.
one unfortunately does not. This is why
So-
actually, yeah.
Yeah,
Yeah,
so I was just wondering, like, is the new conditions, because like we don't get the details, so I'm not quite sure. Are the 2 conditions, the new conditions, harder to check, or they're easier to check?
Unfortunately, they are harder to check. In
I
fact,
see.
it actually, this condition decreasing, this condition implies both these 2 conditions. But these 2 conditions are more general and harder to check. Yeah.
I see.
Yeah. So that's why we need to put more effort to prove the Stanley's inequality. Thanks for the question. Any other question? If no, then yeah, I think that's the end of the class. And thank you so much again for hosting me for the next for the last 3 classes. And I will
Thank
see
you
everybody.
so much. It's really, really good. That's
Thank you.
the speaker again.
Thank you so much.
Yeah, so we'll be back on Thursday, and that will be our final IPAC seminar. So hope to see everyone. All right. Have a nice day, everyone.
Bye-bye.
Bye. Thank you.
Thank you.